It begins with a darkness unlike any other. Not the gentle darkness of midnight skies scattered with starlight, nor the comforting shadow of a moonless night, but an absence so complete it swallows thought itself. In the vast cartography of the cosmos, where astronomers trace the delicate threads of the galactic web, there is a place where those threads unravel entirely, leaving nothing but an ocean of black. To the human eye, it would look as though the universe itself had simply forgotten to exist there. No glimmering galaxies, no faint wisps of nebulae, not even the cold spark of a distant star. It is an expanse that should contain 1,000 galaxies, each teeming with hundreds of billions of stars, yet it holds only silence and emptiness. The first time the coordinates appeared on astronomers' charts, there was hesitation. Mistakes happen. Instruments misfire, sensors drift, data gets smeared by cosmic dust. Surely this was nothing more than an observational error. But when the same measurements returned again and again from different telescopes scattered across the world and in orbit, the truth began to press in. There was nothing there. The data, stubborn and unyielding, spoke with the voice of the void itself. The more they looked, the more this absence grew, not in size, but in significance. For in a universe governed by the rules of gravity and matter, such a wound in the cosmic fabric should not exist. Imagine charting a desert from space. From orbit, the dunes stretch endlessly, but here and there you find an oasis, a river, a scattering of green. The galaxies of our universe are those oases, clustered in vibrant communities along invisible highways of gravity. Between them, there are always spaces, but those spaces are thin, interlaced with threads of matter too faint to see without the sharpest instruments. The place at the heart of this mystery, however, is not merely an empty stretch of desert. It is a chasm so deep, the sands themselves have fallen away. The human mind resists the idea of absolute nothingness. Even in the barren reaches between galaxies, there is still the faint breath of hydrogen atoms, the flicker of photons from the early universe, the steady pull of dark matter's invisible hand. But the cosmic void that now drew astronomers' attention seemed to defy even this minimal inheritance of creation. It was not just sparse, it was profoundly absent, as if the laws that built stars and galaxies had been revoked in this one place. This is no small hollow pocket, no minor fluctuation in the cosmic weave. It stretches hundreds of millions of light-years across, an expanse so vast it could swallow the entire Milky Way thousands of times over and still have room for countless other galaxies. To travel from one edge to the other, even at the speed of light, would take longer than the age of many of the stars we see in the night sky. It is a scale that resists metaphor, that outpaces comprehension. And yet, to astronomers, it is as tangible as the air we breathe. There is a kind of quiet dread in contemplating such a place. In the glow of city lights, under a dome of pale atmosphere, the night sky seems infinite, crowded with stars. But the reality is far more fragile. Space is mostly empty, and what we think of as the abundance of stars is only a thin frosting on an ocean of black. To find a region where even that thin frosting has been scraped away is to stand at the edge of a cliff and look down into a depth that offers no bottom. The discovery was not greeted with excitement alone. There was unease, the kind that settles in when the map you trusted reveals a hole large enough to swallow continents. In science, anomalies are opportunities, but they are also warnings. Something in our understanding is incomplete. Perhaps the void is a quirk of random chance, an improbable fluctuation in the early universe's distribution of matter. Or perhaps it is a sign of something stranger, something that does not belong to the familiar logic of cosmic evolution. For the layperson, it is tempting to think of this void as a kind of space between the spaces, a natural consequence of the universe's expansion and structure. But the astronomers studying it know better. The cosmic web is balanced between emptiness and fullness, shaped by the interplay of gravity, dark matter, and the ripples left over from the Big Bang. Voids exist, yes, but they are not like this. This one is too large, too clean, too absolute. The universe does not often make perfect circles of absence. In the cold glow of control rooms, images of the void cycle endlessly on computer screens. Plots of galaxy positions show every dot, every smear of light, except in the region at the center of the mystery. There, the map falls silent. The absence takes shape in negative space, a hollow in the great sculpture of the universe. It becomes impossible not to imagine what could cause such a thing. The mind reaches for answers, gravitational anomalies, interactions with unknown forces, the shadow of something vast and invisible pressing against our own universe. In the silence, possibilities multiply. The human journey into the stars has always been a search for connection, for the places where life and light can emerge. The discovery of this void is the opposite. It is a confrontation with separation, with the possibility that parts of the cosmos are not merely empty, but fundamentally unwelcoming to the formation of anything at all. The void is not hostile. It does not need to be. Its very nature is exclusion. As the story unfolds, it will become clear that the cosmic void is not just a scientific puzzle, but a philosophical one. What does it mean for a universe to hold such perfect silence in its heart? What does it say about the balance between creation and erasure? For now, the only certainty is that this place should not be as it is, and yet it is. The void waits, vast and patient, holding its secrets just beyond the reach of light. In the grand tapestry of the universe, the galaxies do not float aimlessly like scattered sparks from a fire. They are arranged in a structure so intricate, so immense, that it defies every scale the human mind has ever known. To map it is to confront a kind of beauty that exists far beyond our world, a beauty woven from gravity, time, and matter itself. Astronomers call it the cosmic web, a vast network of filaments and nodes where galaxies gather in shimmering clusters, separated by gulfs of relative emptiness. It is not chaos, but an architecture, an invisible framework upon which the luminous matter of the cosmos is draped. Imagine a single drop of ink falling into a glass of water, tendrils curling and branching outward in delicate, twisting patterns. That is the universe on its largest scale, except that the filaments of the cosmic web stretch not for centimeters, but for hundreds of millions of light years. Within these filaments are the great galaxy clusters, cities of stars, each containing trillions of suns, drawn together by the slow, inexorable pull of gravity. Between them lie the cosmic voids, dark stretches where the density of matter falls away. These voids are like the quiet plains between mountain ranges, empty compared to the peaks, but still shaped by the same forces. The mapping of this grand structure is one of humanity's most ambitious acts of cartography. We cannot travel there in ships or send probes to chart it. Instead, we gather light. Every photon captured by a telescope is a message from the past, carrying the position of a galaxy across the abyss of time. Thousands, then millions, of such points are recorded, each plotted into three-dimensional maps that turn random specks into a coherent design. When these maps are rotated and studied, the filaments emerge, graceful arcs, twisting strands, and luminous knots, forming the skeleton of all we know. The act of mapping is not passive. It is a hunt. Astronomers design surveys like hunters, laying out nets across the sky, selecting target regions, and painstakingly cataloging each galaxy. The Sloan Digital Sky Survey, one of the most ambitious of its kind, became a kind of treasure map, revealing structures larger than anything previously imagined, walls of galaxies stretching 1 billion light-years, rivers of matter feeding into superclusters, and voids so large they seemed almost artificial. It was in the context of these surveys that the void at the heart of this story first appeared, an absence so abrupt and so perfect that it disrupted the continuity of the web. From a distance, the cosmic web appears balanced. Every great cluster of matter is paired with a counterweight of space. This equilibrium is no accident. It is the outcome of nearly 14 billion years of gravitational negotiation, shaped by the seeds sown in the first fractions of a second after the Big Bang. The universe began almost uniform, with only the slightest variations in density, variations so slight they were etched into the afterglow of creation itself, the cosmic microwave background. Over time, these tiny differences grew, with dense regions drawing in more matter, forming galaxies and clusters, while sparse regions became the voids. But the void we now focus on does not fit neatly into this pattern. It is not merely a region of low density, it is a place where the filamentary strands of the web seem to break, leaving nothing to connect one side to the other. On the maps, it looks like a great hole punched through the universe's architecture, as though some unseen hand had swept it clean. The surrounding filaments curve around its edges, as if respecting a boundary they cannot cross. To astronomers, accustomed to the smooth ebb and flow of cosmic structure, this sharp absence is jarring. The process of locating it in 3 dimensions is a feat of patience and precision. Each galaxy's redshift, the stretching of its light as the universe expands, reveals its distance from Earth. Layer by layer, astronomers peel back the depths of space, building a volumetric picture of the cosmos. In the void's coordinates, this picture shows nothing but darkness. Not an isolated gap, not a trick of perspective, but a sustained emptiness across hundreds of millions of light years. Even in the context of cosmic mapping, there is something almost intimate about the way scientists come to know such a place. The data sets are immense, but they are handled by human eyes and minds, each chart and plot examined, debated, and compared. At times, the void seems to take on a personality, not of malice or purpose, but of singularity, a feature of the universe that refuses to blend into its surroundings. It is both part of the web and apart from it. There is a kind of paradox here. Without mapping the cosmic web, such a void would be invisible to us, indistinguishable from any other dark patch in the night sky. Yet, once seen in the context of the whole, it becomes the most glaring feature in the chart, a space so vast it challenges the elegance of the structure around it. The web is meant to be continuous, its filaments crossing space like the roots of a great tree. The void is a severed root, a silence in the song of gravity. As the maps become more detailed, the void's outline sharpens. Its boundaries are not neat, they ripple and bulge, shaped by the distribution of the surrounding matter. But in every rendering, it remains unmistakable, a region of almost pure absence. This is not the emptiness of the human imagination, a blank sheet awaiting a story. It is the emptiness of a story already written, a chapter removed from the book, leaving only the binding where the pages should be. Standing at the edge of such knowledge is humbling. To map the cosmic web is to glimpse the universe's grand design, to see the invisible forces that have shaped everything from the birth of galaxies to the rise of life on Earth. Yet, within that design lies this imperfection, or perhaps this perfection of another kind, a reminder that even on the largest scales, the universe is capable of surprises. The void is not an absence in our map, it is an absence in the universe's own blueprint. In the next step of the journey, the focus will narrow from the grand sweep of the cosmic web to the moment when human eyes first glimpsed this place for what it was. The story of discovery is as much about the persistence of those who searched as it is about the void itself, for only by daring to look into the deepest darkness could they reveal the outline of nothingness. It began as so many great discoveries do, not with a sudden revelation, but with a faint whisper in the data. Late nights in observatories often blur together, rows of glowing monitors, the hum of cooling fans, the quiet shuffle of papers. But on this night, the air was different. A cluster of astronomers sat hunched over the latest results from a deep sky survey, their eyes scanning a field that should have been brimming with distant galaxies. Instead, they saw nothing. A blankness where the chart insisted there should be light. At first, no one spoke. Such anomalies were not rare. Instruments misaligned. Processing algorithms miscalculated. Cosmic dust or faint gas clouds sometimes obscured even the brightest targets. The natural instinct was to assume error, to find a flaw in the method. But as the minutes passed and the data was checked against multiple sources, that explanation began to fray. They were not looking at a glitch. They were looking at a truth. The first to break the silence did so in a tone both hesitant and electric. "There's nothing here." The others leaned in. Cross-references were made with older star catalogs. Digital overlays were adjusted. Images from different nights and different telescopes were brought into view. The emptiness held. Even when filtered for the faintest of signals, the space remained black. Astronomers are trained to mistrust the dramatic. The universe is a patient storyteller, and apparent surprises often turn out to be familiar phenomena seen from an unfamiliar angle. But here, the longer they looked, the more unusual the picture became. This was not an isolated patch of sky missing a few galaxies. It was a vast expanse, an entire region seemingly erased from the map of existence. The realization brought a strange mixture of feelings: wonder, certainly, but also unease. Space is not supposed to have such clean absences. Even the darkest reaches of intergalactic space usually sparkle faintly with galaxies billions of light-years away. Yet this view was pure and unbroken darkness, as if some invisible curtain had been drawn across the stars. Word of the anomaly spread quietly at first, carried in email threads between research teams, mentioned in passing over coffee between colleagues. Most dismissed it politely, assuming it was a statistical oddity that deeper surveys would fill in. But those who had seen the raw data knew better. They had already double-checked it with independent instruments. The gap was real, and it was enormous. There is a moment in discovery when scale becomes the most unsettling fact. When the team calculated the size of the void, their sense of proportion shifted sharply. Hundreds of millions of light-years in diameter, larger than the great walls and superclusters that define the cosmic web. It was a whole, not just in the distribution of galaxies, but in the architecture of the known universe. Such a feature should be nearly impossible, and yet here it was, hiding in plain sight. The more they examined it, the more questions emerged. Was it a natural result of cosmic evolution, a rare but plausible fluctuation in the density of matter? Or was it a sign of something beyond current theory, a scar left by forces the universe had not yet revealed to us? The absence seemed almost deliberate in its perfection, as though some boundary had been drawn and enforced by an unseen hand. Late-night discussions began to take on a different tone. Some researchers spoke cautiously of exotic explanations, interactions with other universes, effects of unknown forms of energy, even speculative notions that the void might be a remnant of events predating the Big Bang itself. Others resisted, preferring the safety of known physics, insisting that such ideas belonged in philosophy, not astronomy. But all agreed on one point: this was no ordinary patch of empty space. The images from those first observations remain haunting. In false color maps, the surrounding regions glow with the steady light of thousands of galaxies, but in the center is a darkness so absolute, it seems to pull the eye inward. The edges are not abrupt. There is a subtle gradient where galaxies grow fewer and fainter, as though falling away from some unseen center. To gaze at these maps is to feel the pull of curiosity and the chill of standing before something that does not yield its purpose. For the astronomers who had been there at the start, the void became a kind of obsession. They returned to it again and again, scanning it with every tool available: radio arrays, infrared detectors, the most sensitive optical telescopes. Each instrument confirmed the same thing: absence. It was not an illusion caused by intervening dust, nor the shadow of a foreground object. The void was simply there, vast and unfilled. In time, the discovery moved from whispered speculation to formal announcement. Papers were written, data sets published, conferences convened. As often happens, the wider scientific community greeted the news with both fascination and skepticism. The void's existence was not in doubt. By then, it had been confirmed independently multiple times, but its origin was a matter of fierce debate. Some argued it was the inevitable result of random clustering over cosmic time. Others saw it as a statistical outlier so extreme that it hinted at something deeper, perhaps even unknown laws of physics. For the public, the idea took hold in more poetic terms: the great nothing, the cosmic scar, the black desert. Popular articles described it as a place where the universe had forgotten to create, a wound in the fabric of reality itself. Artists rendered it as an endless cavern in space, a mouth without a voice, a silence given form. In the realm of imagination, the void quickly became more than a scientific curiosity. It was a symbol, a reminder that not all mysteries lie beyond the reach of observation. Some sit plainly in our maps, daring us to explain them. As the data deepened and the models grew more precise, one truth became undeniable: the first glimpse was only the beginning. The void's sheer scale and peculiar properties meant that any answer would have consequences for our understanding of the universe as a whole. It was not just a gap in the stars, but a challenge to the very principles that govern their arrangement. And so, what began as a faint absence in the charts became an epicenter of inquiry, a darkness not to be avoided, but to be explored. The first realization was that seeing the void was not the same as knowing it. A patch of black on a survey map could be deceptive. The human mind is quick to underestimate scale when faced with emptiness. Measuring such an absence would require peeling back the layers of the universe, translating light into distance and distance into size, until the numbers themselves threatened to slip beyond comprehension. Astronomers approached the task with the precision of architects and the patience of archaeologists. Every galaxy on the edge of the void became a reference point, each one a fixed pin in an invisible grid stretching across billions of light-years. They charted these anchors meticulously, noting their coordinates, redshifts, and relative velocities. By mapping the outer rim of presence, they could begin to trace the inner outline of absence. The primary tool was the measurement of redshift, the stretching of light toward the red end of the spectrum as galaxies recede with the expansion of the universe. Each galaxy's redshift is a clock ticking backward through cosmic time. By measuring it, astronomers can determine how far away a galaxy lies, not in miles or kilometers, but in light years, the distance light travels in a single year. The galaxies bordering the void all shared a curious alignment in distance, as though they formed the lip of a vast unseen bowl. Layer by layer, the shape began to emerge. This was no narrow gap, no minor irregularity in the cosmic web. The void sprawled across hundreds of millions of light-years in diameter, so large that, if the Milky Way sat at its center, even the nearest galaxies in our local group would be swallowed whole by its emptiness. The Great Wall, one of the largest known structures in the universe, would barely stretch across a fraction of its breadth. The numbers were staggering: 400 million light-years. Then 500. Some estimates, depending on the precise method used, pushed the figure closer to 600. This was not just large, it was unprecedented. The largest voids in previous surveys had been mere shadows compared to this. Statistically, such a feature should be vanishingly rare, perhaps unique in the observable universe. The models that predicted the natural formation of voids began to strain under the weight of this single example. The process of confirming these measurements was painstaking. Data from multiple surveys, the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and others, were cross-referenced. Radio telescopes scanned for hydrogen emissions that might betray the presence of faint, hidden galaxies. Infrared arrays probed for the soft glow of ancient stars. In every case, the void remained stubbornly dark. Even the background radiation of the cosmos seemed subtly altered when passing through it, hinting at its true immensity. For those working with the data, the experience was surreal. The mind could handle the concept of a star, a galaxy, even a cluster. These had shapes, edges, colors, a presence. But a structure defined by absence was something else entirely. It was like trying to measure the depth of a shadow or to weigh the air in an open plain. Every number was an act of inference, built from the things that were there rather than the thing itself. As the measurements became more refined, astronomers began to map not just the void size, but its geometry. It was not a perfect sphere, nor a simple ellipse. Instead, its boundaries undulated, curving and stretching where the surrounding filaments of galaxies pulled against it. In some places, narrow tendrils of matter reached into its depths like the fingers of a hand probing a hollow. In others, the edge was sharp and clean, as though the void had pushed back, holding the rest of the universe at bay. The sheer scale of the void demanded new ways of thinking about cosmic structure. Gravity operates slowly over such distances, shaping the dance of galaxies across billions of years. If a void this size had formed naturally, it would have taken nearly the entire age of the universe to grow so large. And yet the universe's expansion should have diluted such structures long before they reached this magnitude. Something about this one had allowed it to grow, and to persist. This tension between observation and theory created a quiet undercurrent of unease in the scientific community. If the void size could not be reconciled with current models, then those models were incomplete. Perhaps there was a subtle bias in the way surveys detected galaxies. Perhaps our understanding of matter distribution in the early universe was flawed. Or perhaps the void was not a product of ordinary cosmic evolution at all. To communicate the scale to the public, astronomers reached for analogies, though none seemed sufficient. Imagine emptying the entire volume of thousands of galaxy clusters into a single space and still finding it barren. Picture a sphere so large that light from one side would take 500 million years to reach the other. These were numbers that belonged to the realm of abstraction, and yet they described something real, a place whose edges could be mapped and whose influence could be felt. There was a strange beauty in the act of measuring something so profoundly empty. The very effort to pin down its dimensions was an assertion of human curiosity against the silence of the cosmos. Every data point, every plotted coordinate, was a small act of defiance, a way of saying, here is the nothing and here is where it ends. The final figures were not perfect. In astronomy, they rarely are. But they were consistent enough to reveal the void's place among the largest structures in the known universe, if indeed it could be called a structure at all. It was more like the negative of a structure, the shadow cast by the universe's own architecture. And yet, in that shadow, there was information. The size, the shape, the distribution of the galaxies around it, all hinted at forces and histories still hidden from view. By the time the measurements were complete, the void was no longer just a curiosity. It had become a problem to be solved, a riddle posed by the universe itself. Its dimensions were now known, but its nature remained elusive. And as astronomers turned their attention to its effects on the surrounding cosmos, they began to suspect that the void story was not confined to its own emptiness. Its presence might ripple outward, altering the motion of galaxies far beyond its borders. The next chapter in this investigation would not simply be about what the void was, but about what it did. And in that search, the scale of the mystery would grow even larger. The universe is never still. From the smallest grains of cosmic dust to the largest superclusters of galaxies, everything moves. Some motions are violent, stars exploding, galaxies colliding, while others unfold with a slowness that defies ordinary perception, the drift of matter across billions of years. But all of it is governed by the same invisible architect, gravity. In the cosmic web, gravity is the weaver's hand, drawing threads together, bending paths, shaping the grand tapestry. And where gravity's pull is absent or reduced, a different pattern emerges, a flow not toward something, but away. The void, vast and empty, is not a silent spectator in the universe's dance. Its very emptiness becomes a force of its own. In the same way that a valley draws water downhill, regions of high density pull galaxies toward them. Conversely, a void is like a high plateau in the fabric of gravity, a place where the pull is weaker, where galaxies slip away toward more crowded regions. The result is a slow migration, a cosmic wind of matter flowing around and away from the emptiness. Astronomers have learned to map these flows by studying the peculiar velocities of galaxies. A galaxy's motion is not simply the result of the universe's expansion, it also carries a unique drift, shaped by the gravitational landscape around it. By measuring how galaxies are moving relative to the cosmic background, scientists can trace the contours of this invisible terrain. And in the case of the Great Void, those contours curve sharply, as though space itself is flowing like water around a rock. This phenomenon is sometimes described in terms of cosmic repulsion, though it is not a true force in the sense of gravity or electromagnetism. The void does not push, it fails to pull. The absence of mass inside means there is less gravitational tug to counterbalance the draw from surrounding structures. Galaxies near its edge feel the stronger attraction of distant superclusters and drift toward them, leaving the void emptier still. Over time, this creates a feedback loop. The less matter inside, the less likely it is that matter will enter, and the more pronounced the void becomes. On the grandest scales, these flows are breathtaking in scope. Imagine a swarm of galaxies, each a luminous island of hundreds of billions of stars, all subtly bending their paths to skirt a darkness they cannot see. The effect stretches across hundreds of millions of light years, shaping the routes by which matter travels through the universe. The Great Void is not merely an absence, it is an obstacle in the currents of cosmic motion. In computer simulations, the movement is rendered with exquisite clarity. Filaments of matter stream like rivers, feeding the great galaxy clusters, while the void yawns in their midst, diverting the flow. The patterns resemble the circulation of air currents around the eye of a hurricane, still in the center, furious at the edges. But here, the storm is made of time and gravity, and its lifespan is measured not in hours or days, but in eons. The influence of the void extends far beyond its borders. Galaxies that lie hundreds of millions of light-years away still feel its effect, their paths subtly altered over cosmic time. This has led to the concept of bulk flow, the collective motion of galaxies across vast regions of space. In some areas, the bulk flow appears to point away from the void, as though the emptiness itself is shaping the migration of entire clusters. There is a poetry in this, the nothingness that pulls nothing, yet shapes everything around it. It recalls the way a hole in a riverbed changes the current, not by acting upon the water directly, but by altering the space through which the water moves. The void is not an active player, it is the absence that defines the game. These flows also offer a way to study the void's true boundaries. In a universe that is expanding everywhere at once, it can be difficult to define the edges of something so amorphous. But the motion of galaxies is a more faithful guide than mere coordinates on a map. Where the flow bends, where galaxies begin to turn away, there the void's influence is strongest. By tracing these subtle arcs of movement, astronomers can chart the unseen borders with remarkable accuracy. The motion around the void is not uniform. In some directions, the pull from massive superclusters is strong enough to whip galaxies into long, curving streams. In others, where the surrounding density is lower, the drift is gentler, more diffuse. This asymmetry adds another layer of mystery, hinting that the void is not a solitary feature, but part of a larger gravitational landscape connected to other voids and clusters in ways we have yet to fully map. To the untrained eye, these motions might seem irrelevant, occurring on scales so immense that they have no bearing on our lives. But they are part of the same story that brought matter together to form stars, planets, and eventually life. The void's gentle shaping of the cosmic flow is a distant echo of the processes that set the Milky Way on its course billions of years ago. In a universe where gravity sculpts the future, the absence of gravity sculpts it too. For scientists, the study of these flows is both technical and philosophical. Technically, they offer a chance to test models of large-scale structure formation, to compare simulations with reality, and to refine our understanding of how matter organizes itself over cosmic history. Philosophically, they remind us that the universe is not simply a collection of objects, but a network of relationships, motions, and influences that stretch invisibly across unimaginable distances. In the case of the Great Void, those relationships raise questions that reach beyond motion itself. How did such a massive emptiness come to be? Was it shaped solely by the physics we know, or does it bear the imprint of something stranger, something not yet discovered? The patterns of motion it creates may be the only clues we have to its origin, whispers in the gravitational field that speak of an ancient story written in the dark. And so, the void is not static. It is a participant in the great migration of matter, an unseen architect of the universe's motion. Around it, galaxies slide past like ships avoiding the calm center of a windless sea. They do not stop to linger. They are drawn elsewhere, to the bright cities of the cosmos, where gravity is strong and matter abundant. The void remains behind, patient as stone, its influence felt but never seen, its shape traced only in the paths left by those who pass it by. In 2004, astronomers studying the faint afterglow of the Big Bang noticed something peculiar, an anomaly so strange that it defied simple explanation. The cosmic microwave background, or CMB, is a nearly uniform bath of radiation left over from the universe's earliest moments, a relic from when the cosmos was only 380,000 years old. Across the sky, it appears almost perfectly even, with tiny temperature variations, mere thousandths of a degree, mapping the seeds of all future galaxies. But in one region, they found a patch far colder than expected, a sprawling zone of diminished energy unlike anything else in the cosmic panorama. This became known simply as the cold spot. It wasn't just a statistical blip. The cold spot covered an area of sky nearly 10 degrees across, so large that if you held your hand at arm's length, it would take more than 20 fists to span it. That sheer size was unsettling. According to the most accepted models, such large-scale fluctuations in the CMB should be exceedingly rare. And yet, here it was, sitting quietly in the southern hemisphere of the sky, as though some unknown hand had brushed a shadow across the oldest light in the universe. The first question was obvious. Could this be an artifact, a glitch in the data? Astronomers triple-checked their instruments, recalibrated detectors, and compared readings from different satellites. The cold spot persisted. Even more troubling was that it wasn't just a slightly dimmer patch. It was colder by about 70 microkelvins, enough to stand out sharply in the CMB's delicate pattern. If the CMB is the fossil light of creation, then any large-scale anomaly in it must be telling us something fundamental about the universe's structure or history. Some scientists proposed exotic explanations. Perhaps the cold spot was evidence of a collision between our universe and another, a cosmic bruise left over from when two bubble universes grazed each other in the early inflationary epoch. Others went further still, suggesting it might be a hint of new physics beyond the standard cosmological model, a signpost towards something we had yet to imagine. But there was another, less exotic possibility, one that tied the cold spot to the vast structures of matter and emptiness that have evolved since the Big Bang. According to this idea, the cold spot might not be an intrinsic feature of the CMB at all. Instead, it could be the result of the light's long journey to Earth, a journey that took it through enormous expanses of space shaped by gravity and the distribution of matter. This is where the Great Void entered the picture. In 2015, astronomers using large-scale galaxy surveys noticed that the direction of the cold spot aligned suspiciously well with the location of one of the largest known voids in the nearby universe. The match was uncanny. The thought was that, as the CMB photons passed through this immense underdensity, they would lose a small amount of energy through what's called the integrated Sachs-Wolf effect. In simple terms, the photons enter a gravitational well, or hill, their energies shift, and in the case of a void, they can end up slightly cooler when they emerge. Over a span of hundreds of millions of light-years, even a minuscule effect could leave a measurable imprint. If true, it meant the cold spot might not be a primordial mystery but rather a byproduct of the cosmic landscape, a shadow cast by the emptiness of the Great Void onto the oldest light we can see. But the story wasn't that straightforward. For the Great Void to account for the cold spot entirely, it would have to be unimaginably large, larger than most simulations predicted could form in the universe's lifetime. Some studies suggested that while the void could contribute to the cold spot's appearance, it likely wasn't enough to explain the anomaly in full. The result was a tantalizing middle ground. Perhaps the cold spot was partly shaped by the void, but not entirely born from it. This halfway answer only deepened the intrigue. If the void was responsible for part of the cold spot, then what was responsible for the rest? Was it possible that we were seeing a layered effect, part gravitational, part primordial, woven together across cosmic time? Or was the cold spot simply the universe playing tricks on us, a rare statistical fluctuation amplified by a chance alignment with a massive underdensity? The idea of the cold spot being a cosmic illusion is unsatisfying, but not impossible. In the mathematics of randomness, even extraordinarily unlikely patterns can occur given enough time and space. Yet in science, improbable coincidences often demand explanation. They can be the first hints of something profound. The connection between the void and the cold spot also speaks to a deeper truth about cosmology. The universe is not a static painting but a living story. The light we see from the early cosmos has crossed vast, shifting terrain. Along the way, it has been bent, stretched, and cooled by encounters with gravity's invisible hand. The Great Void, in this sense, is not just a silent emptiness. It is an active participant in shaping the story we read in the oldest light. If the cold spot's origin is indeed linked to the Great Void, it would mean that, even in its absence of matter, the void has left a mark on the most ancient signal we possess. It would be a reminder that emptiness is never truly inert. Like a hollow in the landscape that changes the course of the wind, the void alters the passage of light, leaving its faint fingerprint on the fabric of the cosmos. And yet, there remains the whisper of something more. If part of the cold spot cannot be explained by known physics, it could point toward a chapter of cosmic history we have not yet uncovered. Perhaps it is a relic from before the first galaxies formed. A frozen echo from a time when the laws of physics themselves were still taking shape. Or perhaps it is the faint scar of another universe brushing against our own. A meeting so ancient that only the light of the Big Bang still carries its trace. The cold spot, like the void itself, refuses to yield to a single neat explanation. Its mystery persists, balanced between the ordinary and the extraordinary, between the possible and the impossible. And as we peer deeper into the universe's past, we must accept that some answers may not come quickly or at all. In science, as in the cosmos, the journey toward understanding is often as infinite as the space we explore. When light leaves its birthplace, it begins a voyage across a universe that is anything but smooth. Space is not a calm, uniform expanse. It is a landscape shaped by gravity's invisible architecture. Massive clusters of galaxies act like mountains, bending and magnifying light through gravitational lensing. But voids, those vast regions nearly empty of matter, act in the opposite way. They are not mountains but valleys, hollow depressions in spacetime. And when ancient light falls into such a valley, it emerges altered, bearing subtle scars of the emptiness it has crossed. These marks are what we call gravitational shadows. The term is poetic, but the phenomenon is precise. A gravitational shadow is not darkness in the usual sense. There is no object blocking the light. Instead, it is a change in the light's properties caused by passing through a massive, or in this case, an unmassive, region. In the case of the Great Void, this effect is counterintuitive. You might expect nothingness to do nothing, yet in relativity even nothing can shape the path of light. Voids are areas where the gravitational pull is weaker than average, where spacetime is slightly less curved. This slight difference has consequences over billions of light years. Imagine a photon leaving the surface of last scattering, the moment the universe became transparent, about 13.8 billion years ago. It travels outward, unimpeded, for eons. Then it encounters the Great Void, a region spanning hundreds of millions of light years, with fewer galaxies than expected. In a dense region, a photon would dive into a gravitational well, gaining energy as it falls in and losing it as it climbs out, usually ending up with the same total energy. But in a void, the gravitational hill is actually shrinking over time because the universe's expansion is accelerating. This means the photon loses slightly more energy climbing out than it gained falling in. Over such distances, the effect is cumulative, a subtle but detectable cooling of the light. It is in this way that the void casts its gravitational shadow on the cosmic microwave background, a whisper of interaction between ancient light and modern emptiness. This is the integrated Sachs-Wolf effect in action, a conversation between photons and the evolving geometry of spacetime itself. The Great Void shadow is unusual not only for its scale but also for its clarity. Most voids produce signals so faint that they blend into the noise of the universe's randomness. Yet here, the alignment with the cold spot is too precise to ignore. It is as though this one shadow has been painted with a heavier brushstroke, making it stand out against the vast canvas of the cosmos. Still, a shadow can mislead. Shadows are shaped not only by the object that casts them but by the light that falls upon them. If part of the cold spot is indeed this gravitational shadow, it tells us something remarkable. The void is large enough, and its geometry distinct enough, to influence the universe's most ancient light in a measurable way. That is a clue to its size, its depth, and perhaps even its history. And yet, there's a lingering unease. Gravitational shadows alone, according to the most careful calculations, should not produce the entire cold spot signature we observe. This is where the scientific debate sharpens. Is the void amplifying a pre-existing fluctuation in the cosmic microwave background? Or is it merely aligned with it by coincidence, giving the illusion of a cause and effect relationship? The answer is buried in the mathematics of cosmology, where probabilities and patterns intertwine in a delicate game of interpretation. The philosophical implication is profound. If the cold spot is partly a shadow, then the light we see is not just a message from the past, It is a collaboration between past and present. It is shaped both by the moment of its origin and by the landscapes it has crossed on its way to us. Every photon is not just a messenger, but a traveler, carrying the memory of every encounter it has had along the road. The Great Void, then, is not merely an empty place. It is a co-author in the story of the universe. In the same way that shadows in a room reveal the shape of unseen objects, gravitational shadows may reveal the hidden topography of space-time itself. By studying them, astronomers can map structures too faint to see directly. They can infer the boundaries of the void, the distribution of the galaxies that do exist there, and perhaps even detect the presence of dark matter, or dark energy, in ways that no other method allows. Yet the beauty of this method is matched by its fragility. A gravitational shadow is only as reliable as the model used to interpret it. If our understanding of dark energy's role in expanding the universe changes, so too will our interpretation of the shadow's meaning. This is the tightrope cosmology always walks. Every discovery is provisional, every certainty shadowed by the possibility of new physics. For now, the gravitational shadow of the Great Void remains one of the most compelling pieces of evidence linking it to the cold spot. It is a bridge between theory and observation, a phenomenon predicted by Einstein's equations and confirmed in the faint patterns of ancient light. But it is also an invitation, a sign that there is more to learn, more to uncover, and perhaps more to unlearn about how we think the cosmos works. In the end, a shadow is never the whole object. It is only its outline, a hint of its true form. The Great Void may be more complex than the darkness it casts, more intricate than the cold spot it seems to explain. And until we can step into its depths, not in metaphor but in measurement, we can only trace its edges, following the shape of the unseen through the patterns it leaves on the light of creation. Mapping nothing is one of the strangest challenges in all of science. For centuries, maps were instruments of possession. They showed mountains, rivers, coastlines, things you could stand upon or sail across. To chart the Great Void, however, astronomers must map the absence of such things. This is not like marking unclaimed land on a terrestrial globe. It is like trying to outline a shadow on a cloud. It requires an inversion of thought. Instead of plotting where things are, you must first find where they are not. The first step is deceptively simple: gather the positions of galaxies. Modern surveys like the Sloan Digital Sky Survey have mapped millions of galaxies in 3 dimensions. Each point of light in these maps is a luminous anchor in the cosmic web. Between them lie filaments, thread-like structures where galaxies cluster together under gravity's pull. But in between these threads are yawning spaces where galaxies are few or absent. These gaps are the footprints of voids. The process of identifying a void begins with data that look anything but empty. The raw maps are cluttered with galaxies spread unevenly across the sky. Astronomers apply algorithms to find regions with fewer galaxies than a given threshold, then expand outward until the density rises again. It is a delicate balance. Too strict a threshold and you miss the subtle edges of the void. Too loose and you mistake ordinary sparse regions for something extraordinary. The Great Void stood out because it was both exceptionally large and unusually deep, meaning its galaxy density was far below the cosmic average. But the map of emptiness is more than just a catalog of coordinates. It is a kind of negative image, a photographic plate developed from absence. The boundaries of a void are often ragged, irregular, shaped by the gravitational tug of surrounding structures. They are not perfect spheres as once imagined, but sprawling and asymmetric, each one a fingerprint of the cosmic forces that carved it. Visualizing this negative landscape is where science begins to feel like art. 3-dimensional renderings reveal a universe that looks less like an ordered lattice and more like a sponge, its surface pitted with holes. The cosmic web is the foam, The voids are the bubbles. Yet the bubbles are not truly empty. They contain a faint sprinkling of dwarf galaxies, filaments too tenuous to see without deep observation, and, perhaps most importantly, dark matter and dark energy. Even in absence, the invisible scaffolding of the cosmos persists. For the great void, mapping was both confirmation and mystery. Its sheer size made it stand out from the statistical noise. Its coordinates align suspiciously well with the cold spot in the cosmic microwave background. And yet, mapping alone could not answer whether the void's presence and the cold spot's chill were cause and effect. That required more than geometry, it required physics. Still, the mapping revealed something else, something less tangible but no less striking. In the maps, the great void resembles a hollow in the web, as though a hand had pressed into the cosmic fabric and left a dent. This dent is surrounded by denser regions, a rim of galaxies like a faint shoreline around a dark sea. Some theorists have speculated that this pattern hints at an ancient event, perhaps an uneven distribution of matter in the early universe, or the relic of a collision between cosmic structures before the universe was fully formed. To create such maps, astronomers depend on light's most stubborn property, its willingness to travel for billions of years without losing the memory of where it came from. By collecting spectra from galaxies and measuring their redshifts, scientists can reconstruct not only the positions of galaxies but the history of the space between them. This is how we know the great void is not a trick of perspective. It is genuinely vast and genuinely sparse. And yet, mapping emptiness forces a confrontation with a deeper question. How can we know the full shape of something defined by what is missing? No survey, no matter how complete, sees every galaxy. Some are too faint, others too distant, still others obscured by cosmic dust. The map of the great void, like all maps, is an approximation, a model of reality shaped by the limitations of our instruments. We are sketching in the dark, tracing outlines we cannot fully illuminate. This uncertainty gives the voids a strange dual nature. On one hand, they are real, measurable structures in the cosmic web. On the other, they are partly constructs of our methods and definitions. Change the rules for identifying them, and their shapes shift, their sizes grow or shrink, their significance waxes or wanes. The great void may be singular and special, or it may be one of many we have yet to detect. The map cannot decide, it can only guide. Yet this very ambiguity fuels curiosity. A map of emptiness is not an end, but an invitation. It beckons scientists to explore further, to measure with more precision, to look in wavelengths of light we have not yet exploited. It inspires the creation of next-generation surveys, radio arrays, infrared telescopes, even gravitational wave observatories, that might one day reveal the void's full character. And it challenges philosophers to rethink the meaning of space itself. Is emptiness a thing with properties and behavior of its own? Or is it only the stage on which matter plays out its story? The cartographers of the cosmic web know that their maps are incomplete, and perhaps always will be. But incompleteness is not a flaw, it is the essence of exploration. Each map is a step, each void a mystery waiting to be crossed. The great void, marked now on humanity's cosmic charts, is both a place and a question. It is the largest landmark of nothing we have ever found, and in that paradox lies its beauty. In the end, a map of emptiness tells us as much about ourselves as it does about the universe. We are creatures who cannot resist the urge to draw boundaries, even around absence. We chart the uncharted not because we expect to conquer it, but because the act of mapping is how we turn mystery into meaning. And in the dark heart of the great void, the map is only the first step. What lies beyond its edges is the real journey waiting to be undertaken. Edges have always fascinated humanity. From the earliest maps, where the known world ended in dragons and sea monsters, to the farthest mountain ranges glimpsed by ancient explorers, there has always been a psychological weight to the boundary between the charted and the unknown. In the cosmos, the idea of an edge is far stranger, for there are no walls, no cliffs, no shimmering borders where reality stops. And yet, when astronomers trace the outline of the Great Void, they find themselves staring at a frontier as profound as any in human history, a threshold between the familiar texture of the universe and an abyss where that texture thins to near nothing. The edge of a void is not a clean line. It is a gradient, a slow fading of galaxies until they are scattered like a handful of sparks dying in the night. Here, matter exists, but tenuously. Dwarf galaxies hang like isolated lanterns in a vast dark field, their starlight struggling against the silence. Gravity's pull is weaker here, the cosmic web's filaments grow sparse and brittle. It is the kind of place where you can feel the enormity of scale pressing in, not through the closeness of objects, but through their absence. Crossing into such a region in a spacecraft, if we ever could, would not be marked by fireworks or alarms. Instead, the journey would be almost imperceptible, a gradual dimming of the cosmic scenery. Stars and galaxies would drift farther apart until you could turn in any direction and see more black than light. And somewhere deep within, you would cross a statistical boundary and find yourself inside the void. In a philosophical sense, this is where the known begins to unravel, not because we have no data, but because our theories strain under the weight of absence. The physics of galaxies is built upon the interactions of matter, gravity pulling, light shining, gas collapsing into stars. Remove most of that matter, and you are left with a canvas almost too blank to interpret. Does dark matter cling to the void's edges like frost on a window pane? Does dark energy expand it faster than the universe as a whole? The edge of the known is not merely spatial, it is conceptual. Historically, every frontier humanity has reached has transformed our worldview. Crossing oceans redefined the scale of the planet. Reaching space redefined our place in the solar system. Mapping the cosmic web redefined our place in the universe. And now, probing the void challenges us again, forcing us to confront the possibility that vast stretches of reality are not filled with exotic wonders, but with a profound stillness. This stillness, paradoxically, may be just as important as the bustling regions of galaxy clusters. For in its emptiness, the void reveals the skeleton of the universe, the scaffolding upon which everything else is hung. Astronomers studying the great void often speak of its rim. This rim is where galaxies crowd together, as though the universe itself were gathering around the edges of the abyss. Some models suggest that matter has been flowing out of the void for billions of years, drawn toward these denser regions. The edge is thus not static, but dynamic, a moving frontier where cosmic geography is shaped by gravitational currents. Standing at this edge in your mind's eye, you might imagine a slow cosmic tide, matter streaming away into the brighter realms, leaving behind a deepening hollow. But there is another way to see this frontier, one that turns fear into fascination. The edge of the known is not a dead end, but a gateway. It marks the transition from the loud, crowded parts of the cosmos to the quiet halls where other processes might unfold unnoticed. If exotic physics or rare phenomena exist, they may hide here, free from the gravitational chaos of busy galaxy clusters. Perhaps the void is a laboratory of nature, testing rules we have yet to imagine. The human mind has an uneasy relationship with emptiness. We crave pattern, connection, and narrative. At the edge of the known, the universe offers us none of these comforts. The patterns we see here are faint and fragile, the connections stretched thin, the story nearly silent. And yet, this is precisely why these boundaries matter. They force us to confront the limits of perception. What we cannot yet explain becomes the seed of the next discovery. In the deep past, there was a similar threshold when our ancestors first looked beyond their campfires into the dark forest. The edge was both a danger and a promise. Cross it, and you risked the unknown. Stay behind, and you remained forever ignorant. The Great Void's edge is the modern equivalent, but on a scale so vast that the metaphor almost collapses under its own weight. Here, the forest is an expanse of space millions of light-years across, and the dangers are not predators, but the unsettling possibility that much of the universe is fundamentally unlike the parts we inhabit. Even now, the idea of an edge in a universe without boundaries feels contradictory. Cosmology tells us space is homogeneous on the largest scales, that no region is truly special. And yet, when you stand at the rim of a supervoid in your imagination, it feels special. It feels like a place where the rules might be different, where the thinness of matter might give rise to subtleties we have not yet learned to measure. In this way, the edge of the known is both a physical region and a conceptual challenge to our cosmological principles. From here, the journey into the void becomes an exercise in humility. Our telescopes, no matter how powerful, see only slices of reality. Our theories, no matter how elegant, are provisional. The edge reminds us that beyond the reach of our instruments lies a vast expanse where our maps are vague sketches and our certainties dissolve. And yet, that same reminder is exhilarating, for it means there is still so much to learn. Perhaps this is the true purpose of the edge of the known, not to warn us away, but to beckon us forward. It is the line where knowledge meets ignorance, where data fades into speculation, where the next great leap in understanding may be waiting. For those who dare to cross it, the reward is not just new information, but a deeper relationship with the mystery itself. Standing here, on the brink of the Great Void, you can almost feel the pull. Not the pull of gravity, but the pull of curiosity, the most powerful force humanity has ever known. For most of modern cosmology's history, we thought we had a fairly clear picture of the universe's large-scale structure. The cosmos, it was believed, was like an enormous tapestry woven from threads of galaxies and dark matter, stretching endlessly in every direction. This fabric was not uniform. There were denser knots where galaxy clusters formed and looser threads where space stretched wider, but the variations seemed well understood. The great principle guiding it all was the cosmological principle. On the largest scales, the universe was roughly the same everywhere. No region was truly special, no void was so vast as to defy statistical expectation. Our maps of the universe reinforced this sense of order. Through redshift surveys and painstaking observations, astronomers traced the cosmic web, bright filaments of galaxies laced between sprawling dark pockets of emptiness. These voids, though enormous by human standards, still fit comfortably within the predictions of our models. They were the empty rooms in the mansion of the cosmos, inevitable side effects of gravitational clustering. The universe seemed balanced. For every dense cluster, a void. For every void, a cluster. In this view, voids were not mysterious. They were simply the byproducts of cosmic architecture. Matter had clumped together under gravity over billions of years, leaving behind these vast, undepopulated zones. Dark matter shaped it all, invisible scaffolding guiding galaxies into place, like beads along a string. The equations describing this process had been tested again and again, their predictions matching what telescopes revealed. We thought we knew how the universe carved itself into its intricate shapes. The confidence extended beyond structure. The prevailing lambda-CDM model, the standard model of cosmology, gave us a universe whose evolution could be predicted with astonishing precision. It told us how matter and energy interacted, how cosmic expansion unfolded, and even how the tiniest fluctuations in the early universe's energy density ballooned into the structures we see today. Voids were an expected, well-behaved part of that narrative. Nothing in the theory hinted that we might encounter an empty expanse so large it would stretch our equations to the breaking point. Then came the data that unsettled everything. When astronomers stumbled upon the Great Void, it didn't fit. Not in size, not in depth, not in the statistical comfort zone we had built around our understanding of cosmic structure. This was not a typical gap between galaxy clusters. It was a yawning chasm, hundreds of millions of light-years across, where the density of matter was far below anything our simulations considered likely. By rights, it should have been vanishingly rare, if not impossible. The discovery struck a deep chord because it didn't just challenge a single measurement. It called into question the scaffolding of the whole model. If a void of this magnitude exists, perhaps the distribution of matter in the universe is more irregular than we believed. Perhaps the early fluctuations in the cosmic microwave background were amplified in ways our theories don't account for. Or perhaps the expansion of the universe itself behaves differently in these regions, subtly distorting the growth of structure over cosmic time. Before the Great Void, our mental map of the cosmos was one of smooth predictability. Now, that map has a gaping blank space. And the human mind, wired to seek patterns and order, finds blank spaces deeply unsettling. It's the same unease ancient cartographers must have felt when sketching coastlines, beyond which lay only, "Here be dragons." Our dragons are not creatures, but discrepancies, statistical outliers that threaten the neat harmony of our equations. What we thought we knew also shaped the language we used to describe the universe. We spoke of voids as quiet, unremarkable places, less like abysses and more like the calm spaces between notes in a symphony. The Great Void forces us to reframe that metaphor. This is not a quiet pause, but a deep, resonant silence that makes the surrounding notes sound different. In music, silence can be just as important as sound, and in cosmology, emptiness can carry just as much meaning as matter. The challenge now is to decide whether the Great Void is an anomaly, a cosmic accident that slipped through the cracks of probability, or a clue to something more fundamental. If it is the latter, our standard model of cosmology may need revision, just as Newton's laws once gave way to Einstein's. That prospect is both daunting and thrilling. Theories are not sacred. They are provisional tools, sharpened or discarded as new evidence demands. And sometimes, it takes an emptiness to reveal where our tools are blunt. There is also a psychological layer to this shift. Scientists, like all humans, are drawn to completeness. We prefer a universe that behaves, that rewards our equations with predictable results. The Great Void resists that comfort. It whispers that the universe may be stranger, less orderly, and more capable of surprises than we had hoped. In that sense, it reminds us of the cosmos we first glimpsed when we began looking beyond our planet, a vast, alien expanse that refused to conform to our expectations. And yet, there is a kind of beauty in this disruption. What we thought we knew was a closed door, and the Great Void has forced it open. The light that spills through is not the reassuring glow of certainty, but the stark brilliance of a question mark. In science, that kind of light is precious. It means the story is not over, the final chapter has not yet been written. The shift from knowing to not knowing is not a loss. It is a gain in possibility. The Great Void may hold answers to questions we haven't learned to ask yet. It may force us to rethink the way galaxies form, or even the way space itself expands. In the gap between what we believed and what the data now demands lies the terrain of discovery. What we thought we knew gave us a universe of balance and predictability. The Great Void gives us a universe of contrast and tension, a cosmos that contains both the dense brilliance of galaxy clusters and the profound darkness of near-total emptiness. That tension between fullness and void may be the real shape of reality. And in embracing it, we step closer to understanding not just the universe's structure, but its character. We often speak of the void as if it were an absence, a simple nothing, an empty room in the mansion of the universe. But in physics, nothing is never truly nothing. The very concept collapses under scrutiny, revealing layers of complexity that turn emptiness into one of the most fascinating phenomena in the cosmos. A true vacuum, stripped of matter, light, and even radiation, still seethes with invisible activity. It is a stage on which the universe's most subtle forces are at work, shaping reality from behind the scenes. On the quantum scale, the void is restless. Virtual particles flicker into existence for fractions of a second before annihilating each other, borrowing energy from the vacuum in accordance with the uncertainty principle. This is not poetic imagery, it is measurable. Experiments like the Casimir effect, where two metal plates placed close together experience a force due purely to the vacuum's fluctuations, show that empty space is alive with quantum activity. In a sense, the universe is never silent. Even in its darkest, most barren corners, there is a background hum, the whisper of existence itself. The great void, then, is not an absolute nothingness. It is simply less matter, less light, fewer galaxies, yet it contains the same quantum fabric that pervades all of space. This fabric is threaded with the influences of dark energy, the mysterious force driving the universe's accelerated expansion. In fact, voids may be key laboratories for studying dark energy precisely because they lack the gravitational clutter of massive galaxy clusters. In their openness, they reveal the large-scale tug-of-war between cosmic forces more clearly. When cosmologists speak of nothingness, they often mean a region stripped of matter, but even then, the geometry of space remains. And geometry is not passive. Einstein's general relativity tells us that the shape of spacetime determines how objects move, and in turn, mass and energy determine that shape. In a void, the lack of mass means the curvature is different. It expands faster than denser regions, stretching the galaxies at its borders ever farther apart. This is emptiness as a dynamic player, sculpting the motion of the universe. On the largest scales, this interplay becomes profound. Imagine a cosmic web where the dense filaments are pulled inward by gravity, while the voids swell outward like cosmic lungs inhaling an invisible breath. The physics of nothingness is not static. It is a process, an evolution, a living architecture. Over billions of years, voids grow, merging with one another, reshaping the distribution of galaxies like a slow-motion tide erasing islands from a map. The paradox deepens when we consider that nothingness might be the birthplace of everything. The leading theory of cosmic origins, quantum fluctuations in the early universe, suggests that tiny variations in this so-called empty vacuum were amplified by inflation, seeding all the matter and energy we see today. In this view, the void is not just a backdrop for creation, it is the raw material from which creation emerges. Nothingness gave birth to something, and that something became everything. The great void, then, is more than a hole in the cosmic web. It is a reminder that absence can be as physically real as presence. We tend to privilege matter in our thinking, to treat it as the substance of reality, but in cosmology, structure arises from the balance between what is there and what is not. Voids define the clusters as much as clusters define the voids. Without emptiness, there would be no form, no contrast, no shape to the universe at all. Even the term vacuum becomes slippery when we push the boundaries. Some physicists speculate that our universe's vacuum might not be perfectly stable. In certain scenarios, it could decay into a lower energy state, rewriting the laws of physics in an instant. If true, this would mean that the nothing we live in is not the ultimate nothing. It is a temporary plateau in a deeper landscape of possibilities. A void, in this sense, might be a hint of an even more fundamental emptiness that lies beneath our current reality. From a philosophical perspective, the physics of nothingness challenges our intuition. We imagine nothing as an absence of qualities, but in truth, it is defined by what remains when the obvious is stripped away. In the great void, light is scarce, matter is rare, but the rules of physics still hold sway. Time still passes. Space still stretches. Gravity still whispers across the gulf. Emptiness is not the negation of reality, it is one of its purest expressions. This is why studying voids is not simply an exercise in mapping where galaxies aren't. It is a way of probing the fundamental nature of spacetime itself. Voids magnify the influence of dark energy, expose the scaffolding of dark matter, and provide a kind of cosmic control group for understanding how structure forms. They are the negative spaces in the universe's portrait, and without them, the image would lose its definition. Standing at the edge of the great void, in the mind's eye, one might expect to feel a sense of absence. Instead, there is a strange fullness to the view, a realization that even here, in the loneliest place in the universe, the fabric of reality is taut with hidden activity. The photons that do pass through have traveled almost unimpeded, carrying whispers from distant galaxies. The gravitational pull of nearby filaments tugs faintly at the boundaries, shaping the void's contours. The quantum foam churns invisibly beneath it all. And so, the great void becomes a paradox, the most extreme example of cosmic emptiness, yet still brimming with the underlying forces and fluctuations that make the universe what it is. Its vastness forces us to reckon with the fact that nothingness, as we casually imagine it, does not exist. The void is a place, a structure, a player in the cosmic drama, one that might hold secrets about the origin, fate, and ultimate nature of everything. We entered the study of the great void expecting to find less. Instead, we found a deeper kind of presence, a presence of laws, of geometry, of potential. In that sense, the physics of nothingness is not about the absence of things, but about the persistence of the stage upon which all things play their part. Even in the emptiest depths of the universe, the show goes on. Long before humanity learned to leave the Earth, we learned to measure it. Ancient navigators used the positions of the stars to cross oceans. Farmers read the sun's path to mark the seasons. Priests and scholars charted the heavens in clay, stone, and ink, drawing maps that reflected both wonder and necessity. Today, the tradition continues, but the maps have grown so vast that they no longer describe continents or planets. They describe the universe itself. The task of mapping the cosmos is not a simple act of looking outward. It is a translation of the faintest whispers of light into coordinates, distances, and structures. The cartographers of the modern age do not carry sextants or compasses. They wield telescopes whose mirrors stretch meters across, spectrographs that split ancient starlight into rainbows, and computers that sift through petabytes of data. Their mission is to place every known galaxy in its rightful place, to draw the scaffolding of reality as it truly is. The work begins with light, the one constant messenger across the gulfs of space. By measuring the redshift of a galaxy, how much its light has been stretched by the universe's expansion, astronomers determine its distance. A single measurement tells you little, but millions of measurements, plotted together, reveal the skeleton of the cosmic web, a lattice of filaments and clusters, with voids yawning in between. Each new survey sharpens the image, filling in what was once blank. This is not just an act of curiosity. The distribution of matter in the universe holds clues about its origins, its fate, and the forces that govern it. Mapping the cosmic web is like mapping the currents of a vast, invisible ocean. It shows where gravity has gathered matter into great knots of galaxies, and where expansion has swept space clean. The patterns are not random. They echo the faint irregularities of the early universe, frozen into the cosmic microwave background nearly 14 billion years ago. To chart these structures, astronomers design surveys that span years or even decades. The Sloan Digital Sky Survey, for instance, methodically photographed large swaths of the sky, measuring the positions and spectra of millions of galaxies. Other projects peer deeper, trading breadth for depth, uncovering fainter and more distant structures that push the map back toward the beginning of time. Together, they create overlapping layers of information, like cartographers adding mountain ranges, rivers, and borders to a map that once showed only coastlines. The challenge is not merely collecting the data but interpreting it. Distances in cosmology are slippery. Galaxies do not sit still. They move, tugged by the gravity of their neighbors and the expansion of space. A map of the universe is therefore a snapshot in motion, a picture of where things are, and a hint of where they are going. Even the voids change shape over time, swelling or merging as the cosmic dance continues. Yet for all its technical demands, this work still carries a sense of the ancient. The astronomers hunched over computer screens in quiet observatories are heirs to the same impulse that drove Polynesian navigators across the Pacific or Babylonian priests to trace Venus's path across the dawn sky. They too are trying to find order in the vastness. Their maps are not etched on parchment but in arrays of numbers and coordinates. Still, the instinct is the same. To know where we are, we must know what surrounds us. The most ambitious of these maps go beyond 3 dimensions. They include time itself as a coordinate, reconstructing how the universe's structure evolved over billions of years. By comparing simulations to observations, researchers can rewind the cosmic clock, watching filaments thin and thicken, voids form and grow, clusters collide. These time-lapse maps are not just static portraits. They are living records of a universe in flux. The Great Void occupies a special place in these charts. Its vast, undepopulated expanse stands out as an almost perfect blank in the otherwise tangled web of galaxies. Measuring its size and shape is more than a curiosity. It tests the accuracy of our cosmological models. If the void is larger, smaller, or denser than theory predicts, it may signal something amiss in our understanding of dark matter, dark energy, or the fundamental laws of physics. In this way, the cartographers are also detectives, hunting for inconsistencies in the cosmic blueprint. The data they collect does not live in isolation. It is shared across borders and disciplines, passed from radio astronomers to particle physicists, from supercomputer modelers to telescope engineers. The maps themselves become collaborative works, humanity's collective portrait of the universe, refined year after year. Each dataset is another brushstroke in a canvas that will never be finished, because the universe is too vast and too alive to be captured in a single work. Yet there is beauty even in the incompleteness. Like the old maps of Earth that left entire regions blank with the words "Here be dragons," the edges of our cosmic maps are places of mystery. They mark the limits of what our instruments can detect, the fading horizon where light has not yet reached us. Beyond that, there may be structures even grander, voids even deeper. The map is not the territory, and in cosmology, the territory is always expanding. To create such maps is to bridge an impossible scale. The cartographers translate billions of light years into images and models that can fit on a computer screen or a printed page. They take the unimaginable and make it visible, compressing the history of everything into patterns we can read. In their hands, the chaos of scattered galaxies becomes a network, the abyss becomes a structure, and the universe becomes something we can, if not fully grasp, at least begin to trace. In the end, their work is not just about knowing where galaxies are. It is about situating ourselves in the vast, intricate architecture of reality. Each plotted point is a reminder that we are part of something immeasurable, yet knowable in glimpses. The cosmic cartographers draw not just the outlines of space but the outlines of our own understanding. And in the center of those maps, always, is the tiny mark where we live, a single point in a universe whose edges we have yet to find. The edges of the great void are not abrupt. They are like the shoreline of a fog-bound sea, distant galaxies fading, thinning, dissolving into black. At first, there are still clusters, faint and far apart. Then, like stepping off the continental shelf into the abyss, the galaxies vanish almost completely. Beyond this invisible boundary lies a darkness unlike any other in the cosmos, not because it is empty, but because it is so nearly empty that the mind struggles to comprehend it. To imagine entering the great void is to imagine a journey without familiar landmarks. In most parts of the universe, a voyage of a few million light-years will bring you past thousands of galaxies, each blazing with hundreds of billions of stars. Here, the same journey might bring you past one lonely spiral, its light stretched thin by distance, perhaps a smattering of dim dwarfs barely clinging to existence. The rest is a black so complete that even the most sensitive instruments would see nothing but the afterglow of their own detectors. This is not a darkness of obstruction, like a cave where the light is blocked. It is a darkness born of absence, the result of an almost perfect lack of matter. There is no dust to scatter light, no nearby star to illuminate your path, no galactic neighbors whose gravity might tug at you. The silence is not just figurative, it is physical. Without nearby stars or gas clouds, there is nothing for radiation to strike, nothing for particles to collide with. The very medium of space feels thinner here, as though you are drifting into the purest vacuum nature can create. In such a place, distance becomes abstract. The next galaxy might be hundreds of millions of light-years away, yet in every direction, the view is identical. Up and down, left and right, forward and back lose their meaning. You are surrounded by nothing, and in nothing, there is no reference point. Without instruments, you would have no way to tell if you were moving at all. The concept of speed would dissolve. Only the slow ticking of your onboard clocks would remind you that time is passing. Light, too, behaves differently here, not in its physics, which remain constant, but in its perception. A rare star's light might travel unimpeded for hundreds of millions of years before reaching your eyes. By the time you see it, that star may have aged beyond recognition, or even burned out entirely. Every photon is a time capsule, an echo of a place and moment long gone, arriving across a gulf so great that it feels less like seeing than remembering. For a traveler, the psychological weight of this emptiness would be immense. Human beings evolved in environments crowded with sensory information, the rustle of leaves, the warmth of sunlight, the horizon's curve. Even the emptiest deserts on Earth teem with microlife and shifting wind. The great void offers no such comfort. The only movement is your own. The only light comes from within your vessel. And the only sound is the hum of your machinery, a fragile bubble of order in an ocean of nothing. Yet there is an allure to this silence. Away from the gravitational pull of massive structures, the void offers a stillness unmatched anywhere else in the universe. Space here is smooth, free of the warping that great clusters inflict. It is the closest one can come to a pure, uncurved geometry, a realm where the straight line between 2 points is truly straight for unimaginable distances. In a way, the void is the universe's clean slate, a place unscribbled by the brush of matter. Instruments could take advantage of this clarity. Without the interference of nearby stars or gas, telescopes could peer deeper into the cosmos than almost anywhere else. Ironically, from the center of a void, the rest of the universe becomes more visible. Distant filaments would form a faint, web-like horizon on all sides, glowing softly in the black. The void becomes not just an absence, but a vantage point, a balcony from which to view the architecture of everything that lies beyond. One might expect the temperature here to be lower than anywhere else, but in truth, the cosmic microwave background sets a limit. Even in the heart of the void, the faint afterglow of the Big Bang bathes everything at just under 3 degrees above absolute zero. It is the coldest you can be without cutting yourself off from the universe entirely. The difference lies not in temperature, but in energy. With so little matter around, there are almost no processes to stir heat into motion. The void is a place where entropy has already won. The journey inward would feel endless. Every acceleration would bring no perceptible change in the view. Days and weeks would pass with only subtle shifts in the faint pattern of background galaxies, each one inching apart as the universe continues to expand. It would be like rowing across a lake so large that the shore recedes at the same pace you advance. The deeper you go, the more it feels like the center is always just ahead. For all this, the void is not truly empty. Somewhere in its depths, lone galaxies wander, tiny islands of stars with no nearby neighbors, marooned by the expansion of space. These are called field galaxies, and they live strange, solitary lives. Without the frequent mergers and tidal interactions that shape most galaxies, they evolve in isolation, their spiral arms unperturbed, their star formation slow and steady. To encounter one here would be like finding a solitary lighthouse in the middle of a dark ocean, a reminder that even in the most barren regions, creation has left its trace. Eventually, even those traces fade. Push far enough, and the density of galaxies drops to almost zero. Here, you are as close to nothing as the universe allows. It is a place without purpose, without the usual machinery of cosmic evolution, without even the raw material for new stars. And yet, in its way, it is as much a part of the universe's story as the brightest quasar or the densest cluster. The void is the stage upon which the cosmic web is strung, its silent expanses giving shape to the structures we can see. Standing, or drifting, here, one feels the enormity of that role. The void is not a flaw in the universe's design. It is a fundamental part of it, a reminder that the cosmos is not just built of what is, but of what is not. And in the depths of that absence, the presence of everything else becomes more precious, more fragile, more miraculous than ever before. At first glance, the great void appears to be the purest nothingness the cosmos can offer. But nothing in the universe is truly empty. Even here, in the heart of absence, there is a hidden restlessness. Space itself is never still. Beneath the black surface, the fabric of reality trembles with an invisible dance, particles appearing and vanishing in less than the blink of an eye, energies flickering into existence only to cancel themselves out. This is the quantum vacuum, a sea without waves, yet alive with motion. The human mind has always struggled with the concept of nothingness. Philosophers once imagined a void as a hollow container, an inert backdrop against which matter and light move. Quantum physics overturned that vision entirely. According to its rules, a perfect vacuum is impossible. The uncertainty principle forbids it. Even in the absence of matter, electromagnetic fields fluctuate. Tiny particles, virtual and fleeting, are born and die in fractions of a second. They are not stable enough to be seen directly, but their effects ripple through everything else in the universe. Here in the void, where the density of matter drops to near zero, these quantum effects become more than a theoretical curiosity. Without the noise of nearby galaxies and their storms of radiation, the vacuum's subtle whispers can, in theory, be measured. Space here is like a sheet of still water, in which even the smallest ripple is visible. The smallest perturbation, an incoming particle from a distant supernova, the faint hum of a passing gravitational wave, stands out sharply against the background silence. One of the strangest predictions of quantum theory is that the vacuum itself possesses energy. This so-called zero-point energy exists everywhere, all the time, even in perfect darkness. Its effects may be responsible for phenomena as grand as the accelerated expansion of the universe. Some cosmologists suspect that dark energy, the mysterious force pushing galaxies apart faster and faster, could be nothing more than the latent pressure of the quantum vacuum. If that is true, then the emptiness of the void is not passive at all. It is the very engine of cosmic expansion. This idea reframes the meaning of the void entirely. Rather than being a place where nothing happens, it could be the most active and influential arena in all of existence. The galaxies that populate the filaments are merely passengers on a current driven by forces originating here, in this unseen ocean of quantum fluctuation. What appears still is, in fact, the source of motion for the entire universe. And yet, the quantum vacuum is subtle. Its influence is not something one could feel in the conventional sense. If you floated in the middle of the void, you would not see particles popping into and out of existence like fireflies in the dark. You would feel no push, no warmth, no light. But your instruments, finely tuned beyond anything yet built, might detect minute differences in the vacuum energy from one region to another. Tiny shifts in the way space curves, small tugs from waves of gravity that originated eons ago in the earliest moments after the Big Bang. Some theorists suggest that the vacuum is not uniform. It may have structure, a hidden texture woven into space-time itself. These ideas give rise to bold speculations that the void might be laced with hidden fields, that particles of dark matter might occasionally drift through unseen and unfelt, or that the vacuum energy here could differ slightly from that in denser regions of the universe. If any of these are true, then the Great Void could be a natural laboratory for studying the most fundamental laws of physics, laws that remain invisible in the cluttered, noisy environment of galactic space. To explore such possibilities would require probes capable of surviving in near-absolute isolation for centuries, equipped with detectors sensitive enough to read the faint fingerprints of the vacuum. No spacecraft humanity has built could yet endure such a mission, but the concept is tantalizing. One could imagine a vessel slowly drifting through the heart of the void, collecting data in an environment so still that even the smallest particle strike would be an event worth noting. Over time, it could map the delicate variations in spacetime's tension, revealing patterns hidden from all other vantage points. There is another, more speculative line of thought, that the quantum vacuum might be the birthplace of new universes. In certain cosmological models, fluctuations in the vacuum can trigger inflation, the rapid expansion that marks the birth of a cosmos. If such events can occur once, they could occur again, perhaps in regions far beyond our own observable horizon. In this view, the void is not the end of something but the beginning. It is the seedbed from which other realities might sprout, invisible to us yet governed by the same underlying physics. For travelers, such possibilities would be both humbling and thrilling. Floating in the vast darkness, you might imagine that beyond your perception the very space-time around you is simmering with potential, as if the universe is dreaming in silence. Every cubic centimeter of this emptiness contains the possibility, however remote, of giving rise to something vast and magnificent. The paradox is almost poetic. The most desolate region of space may also be the most fertile in terms of cosmic potential. It is here, far from the bright cities of galaxies, that the universe reveals one of its deepest truths, that emptiness is never truly empty. It is a reservoir, a foundation, a womb. The more one contemplates this, the less the void feels like a dead place. Its stillness is not a lack, but a pause, like the breath before a note in a symphony. It is a silence charged with hidden meaning, an interlude that gives shape to the music of creation. What we call nothingness might be the hidden heartbeat of the cosmos, a pulse too deep and slow for ordinary senses to catch, but steady enough to move the stars themselves. In the end, the void does not diminish the universe's grandeur. It expands it. It teaches that existence is not only about the things we can see, the glowing arcs of galaxies, the roiling nurseries of stars, but also about the unseen stage upon which these wonders perform. The great void, in its quiet, quantum-charged emptiness, is as much a part of the cosmic story as the most brilliant quasar. It is the background hum to which all else is set, a reminder that even in the places where nothing seems to happen, the universe is always ceaselessly becoming. In the great void, light travels for hundreds of millions of years without ever striking a planet, a star, or even a fragment of dust. Here, there are no bustling star fields to drown its journey in glare. Every photon that passes through this silent gulf is a survivor, an ancient wanderer carrying with it the memory of a time long past. Some of this light has traveled since the universe was only a fraction of its current age, having escaped from galaxies that have long since changed shape, merged, or faded. The void is its final undisturbed corridor. The most ancient of these travelers are the relic photons of the cosmic microwave background. They emerged more than 13 billion years ago, when the first atoms formed and the universe's searing fog of plasma became transparent. They have been drifting ever since, stretched by the expansion of space into cold, faint whispers of their former selves. In denser regions of the cosmos, this light is constantly scattered, absorbed, or twisted by matter and magnetic fields. But here, in the open emptiness, it moves in straight, unbroken paths, as if carrying a pristine imprint of the universe's earliest heartbeat. These relic photons are like the faded pages of the oldest book in existence. They tell a story written in the heat of the Big Bang, etched into the temperature variations and polarization patterns they still carry. To detect them in their purest form, one would need to go to places exactly like this, regions where the noise of foreground sources drops to near zero. In the void, there is nothing to obscure the faint lines of that story. Alongside this ancient light drift particles that are even harder to catch, neutrinos. Birthed in the first seconds after the Big Bang, they move almost without interaction, passing through entire galaxies as if they were nothing more than mist. The great void offers no obstruction, no collisions, no distractions. Here, they glide undisturbed, carrying with them information about the universe's first moments that no light can reveal. Their presence is all but impossible to sense without instruments of extreme precision, yet they are here in staggering numbers, forming an invisible tide that never ceases to flow. Gravitational waves too pass through this darkness. These faint ripples in space-time originate from events so powerful they shake the very geometry of the cosmos, colliding black holes, neutron stars spiraling together, and perhaps even the violent fluctuations that marked the universe's birth. While gravitational waves pass through everything, the clarity with which they can be detected depends on the absence of interfering signals. The void offers just such clarity. It is an unspoiled medium where spacetime's subtle quivers remain pure and untangled by the gravitational noise of nearby massive bodies. What drifts through this emptiness is more than relics. It is history itself. Every particle and wave here is a messenger from an earlier chapter of existence. The great void does not merely contain them, it preserves them. It is the archive room of the cosmos, where the records are untouched, the ink unfaded. The only challenge is finding a way to read them. If one could set up a listening post in this darkness, the signals it could collect would be unlike anything recorded near Earth. The faint hiss of the cosmic microwave background would emerge with a clarity that no ground-based telescope could match. Neutrino detectors might, for the first time, directly map the early universe's particle distribution. Gravitational wave observatories could tune themselves to frequencies too faint to detect in noisier regions, opening a new window into epochs we have only guessed at. There is a haunting thought that accompanies such imaginings. Some of the particles passing through the void began their journey before our planet existed, before the sun was born, before the Milky Way even took its current form. They have been moving untouched for billions of years, never slowing, never stopping, as if bound to a promise to carry their ancient truths to wherever they might be read. And here, in the void, their journey is as close to eternal as the universe allows. For explorers, physical or imagined, to drift here is to touch the deep past without moving through time. The silence itself feels heavy, not because it is oppressive, but because it is so saturated with age. Every direction you look is not just space. It is time made visible, time made cold and slow. The stars are distant punctuation marks in an otherwise blank page, each representing a moment in a story that began long before human thought existed to name it. Yet there is also a paradox in this preservation. The very emptiness that allows such ancient messengers to survive also ensures they remain almost impossible to detect. They pass through without leaving a trace, just as they have for billions of years. The void guards its secrets fiercely, not by destroying them, but by keeping them perfectly intact, forever out of reach to all but the most patient and persistent seekers. Still, the possibility of unlocking these archives has driven some of the boldest concepts in modern astrophysics. Imagine a fleet of autonomous instruments, released like seeds into the void, each one silently gathering data for centuries before transmitting its findings back across the light years. With no planets or stars to block their view, these instruments could piece together the most complete and pristine history of the universe ever recorded. They would listen not just to light, but to the faint tremors of space-time itself, to the ghost-like passing of neutrinos, to the subtlest shifts in the cosmic background's temperature. The great void, in this vision, becomes not a place of absence but the ultimate observatory, one where the past is not hidden behind walls of matter or clouds of dust, but laid out in the open, waiting for a reader patient enough to see it. It is the quietest room in the universe, but it is also the most honest. As the centuries pass, the particles and waves drifting here will continue their journeys, some eventually falling into the pull of distant galaxies, others traveling endlessly into whatever lies beyond our observable horizon. But while they cross this vast, unchanging gulf, they are at their purest, carrying the voice of the early cosmos unbroken. And in that voice, if ever heard clearly, may lie answers to questions humanity has asked since it first looked up at the stars. Where did we come from? How did this all begin? And what, if anything, came before? Silence here is not an absence of sound as we know it. In the vacuum of the great void, there is nothing for waves to vibrate, nothing for a human ear to interpret. The silence is total, woven into the very fabric of this place. Yet if silence could have a texture, it would be the kind found here, smooth, infinite, unbroken by the smallest ripple of activity. It is a silence so absolute that it presses against the imagination, demanding to be noticed, refusing to fade into the background. For all the countless processes unfolding across the universe, stars igniting in brilliant firestorms, planets forming from clouds of dust, black holes feeding on the light of surrounding matter, none of it touches this place. The void is exempt from the restless creativity of cosmic evolution. Galaxies skirt its edges but do not trespass into its heart. Even intergalactic gas, the thin haze that connects clusters, is absent here in measurable quantities. It is a rare exemption from the chaos of becoming and undoing. This silence is not merely spatial, it is temporal. Here, events happen with such infrequency that 1,000,000 years can pass without any measurable change. The distances are so vast that even light takes hundreds of millions of years to cross them. In that time, entire civilizations could rise and fall, stars could live and die, galaxies could drift and collide. Yet in the void, nothing would be different. The stillness becomes a form of resistance. Matter that wanders here drifts without purpose, stripped of the gravitational pulls that elsewhere dictate destiny. There are no tidal forces to tear objects apart, no clusters to draw them into intricate orbits. They move only because they began moving, and they will continue until something far beyond the void changes their course. This is Newton's first law written across billions of light years. Even in regions of space that appear empty to the casual eye, there is usually a faint glow, a background of scattered starlight, infrared heat, or the flicker of active galactic nuclei. But here, that glow is stripped away until only the cosmic background remains. In most places, this background is drowned beneath the brighter light of nearby structures. Here, it reigns alone. It is the only voice left, speaking in the dark. In such conditions, time feels stretched, elongated beyond comprehension. Without regular events to mark its passing, the mind, searching for patterns, finds only the repetition of nothing. It is a monotony that is paradoxically rich, because in this unbroken state even the faintest disturbance would stand out like a thunderclap. The collision of two wandering black holes here would be a cosmic drumbeat in an endless symphony of rest. The silence extends beyond what human senses can perceive. There are no magnetic storms to sweep across this space, no particle winds to rattle against invisible boundaries. Cosmic rays, usually born in violent outbursts, thin to a trickle here. The low-energy photons that do arrive are remnants from unimaginably distant origins. They do not announce themselves, they pass through without ceremony. This perfect absence is rare in a universe driven by motion and transformation. It is tempting to think of the void as a wasteland, but that suggests it is somehow incomplete. In truth, it is complete in its own way. Its identity is defined not by what is missing, but by the perfection of its emptiness. It is not a failed galaxy cluster, nor a neglected region of space. It is a legitimate structure of the cosmos, just as fundamental as a star or a planet, though far less tangible. For travelers, whether real or hypothetical, the experience of moving through such a space would be unlike any other. The instruments aboard would record almost nothing, the silence of their readings reflecting the silence outside. The human mind, accustomed to constant stimuli, might struggle to grasp the scale of such emptiness. Hours, days, years could pass without encountering anything to anchor a sense of distance traveled. The stars would seem no closer, no farther, just fixed points in a blackness that refuses to offer clues. In that kind of journey, silence itself becomes a companion, almost a living presence. It is not hostile, but it is absolute. It demands patience, stripping away the expectation of rapid change. 100 generations could cross this space and pass through nothing more eventful than the occasional thin strand of gas, stretched so far that it could not be seen without careful measurement. And yet, this same silence can be deceptive. The absence of events does not mean the absence of significance. The void influences the structures that surround it. Galaxies along its borders are subtly shaped by its pole, or more accurately by the lack of pull from within. They drift away from its center over cosmic time, flowing into denser regions where new stars can form. In this way, the silence at the core of the void helps orchestrate the music beyond it, defining where the crescendos of creation can occur. This shaping effect is slow, almost imperceptible, yet across billions of years it becomes a guiding force. The large-scale structure of the universe, its webs, filaments, and knots, are arranged not just by where matter exists, but by where it does not. The void's silence is therefore not a passive absence, but an active framework, a negative space that defines the positive. Without these immense pockets of nothing, the universe's grand architecture would lose its balance. For those who seek meaning in the cosmos, this challenges the instinct to equate importance with activity. Here, meaning is tied to restraint, to what is left untouched. The great void stands as proof that silence is not the opposite of creation, but part of it, a counterweight without which the whole would be incomplete. If the universe had a moment of meditation, a breath between heartbeats, it would look like this. Here, all motion is background motion. All change is peripheral. The silence is so deep that it could outlast the brightest galaxy's final star. Long after the spirals collapse into faint embers, long after the last planet is stripped bare, the void will remain almost exactly as it is now, still vast and timeless. To witness it is to stand at the edge of an infinite stillness, a stillness that does not end but simply is. And in its presence, the noisy, fleeting life of galaxies seems less like the rule and more like the exception. The universe, it turns out, is not built on endless activity but on a foundation of silence so enduring that everything else, no matter how bright or violent, is merely a brief interruption. Leaving the heart of the void is not a sudden transition but a gradual unveiling. The emptiness loosens its hold so imperceptibly that at first there is no sign of change. The black remains absolute, the silence undisturbed, and the sense of infinite distance unbroken. Yet somewhere far ahead, the first faint traces of structure begin to emerge. They are not immediately visible to the human eye. They are whispers in the data, statistical flickers suggesting that the monotony will not last forever. A faint gradient begins to form, though not in color or brightness as we know it. It is the subtle increase in the number of photons arriving from a single direction, the barely measurable uptick in energy as the darkness yields to something more. Like the slow dawning of a distant shore seen through heavy fog, it is enough to orient motion, enough to awaken expectation. This transition is so stretched across distance that it could take tens of millions of years for a drifting object to cross it. In the early stages, the void still dominates. Vast swaths of space remain barren, and stars are sparse enough to be counted individually. But each passing century adds to the tally. One light appears where before there was none, then another, until the darkness is punctured by a constellation that would be insignificant anywhere else but here feels monumental. The black backdrop softens, not through any change in its hue but through the return of context. A solitary galaxy drifts into view, isolated, dim, but rich in meaning simply because it exists. Its spiral arms, faint and loosely wound, carry the weight of distance in their stretched form. This is a frontier galaxy, shaped by billions of years at the edge of nothing. It has known fewer collisions than its cousins in crowded clusters, fewer gravitational interactions to distort its symmetry. Its stars are older, its gas depleted, and its light subdued, but it holds the unmistakable mark of survival. As motion continues, more such galaxies emerge, scattered far apart, yet bound by the shared experience of living on the void's border. Each one is a lone outpost, sending its ancient light into the abyss behind. Between them, the darkness still yawns wide, but the intervals grow shorter. Patterns begin to form, loose filaments threading between the emptiness, strands of matter pulling toward unseen nodes of gravity. These first filaments are faint, mere suggestions of the vast cosmic web that lies beyond. They stretch like delicate silk across unimaginable gulfs, connecting one lonely system to another. Through them, faint streams of gas and dust flow toward denser regions, carrying the raw materials for future stars. The motion is glacial, the process measured in billions of years, yet its inevitability is certain. With each additional point of light, the environment changes in ways too subtle for the senses but obvious to the instruments. Cosmic rays, absent deep in the void, begin to register more frequently. Their energy signatures tell of active galaxies somewhere ahead, jets of particles launched at near-light speed, perhaps from supermassive black holes in distant cores. Even these indirect signs create a sense of movement toward life, toward complexity. The change also manifests in temperature. The near-perfect uniformity of the cosmic microwave background begins to warp under the influence of localized structures. Slight gravitational distortions bend the paths of ancient photons, producing patterns that speak of mass concentrations too far ahead to yet be seen. The universe is announcing, in its own quiet language, that the emptiness is ending. Eventually, the first true cluster appears, not in physical proximity, for the galaxies are still separated by millions of light-years, but in the mind's understanding. Here are dozens of star cities bound together by their mutual gravity, arranged in a loose association like beads scattered on a thread. Their combined light, faint as it is, forms a landmark in this borderland. It is a threshold, the first clear sign that the great ocean of nothing is giving way to the archipelago of matter. From this vantage, the void behind appears almost like a shadow. Its presence is not forgotten. It lingers as a vast memory in the mind, an echo of stillness. The silence it carried does not vanish immediately. Instead, it becomes a background hum, a contrast that makes every new detail ahead stand out more vividly. As the journey continues, the pace of change accelerates. Filaments thicken, strands of galaxies weave into more intricate patterns, and the spaces between them narrow. The regions of true darkness shrink into pockets, surrounded on all sides by the light of countless stars. Gravitational tides become detectable again, subtly altering the paths of objects, hinting at the immense masses that shape this new landscape. The light from these frontier systems is often ancient, emitted when the universe was younger and the stars within them were still in their prime. To encounter it now is to see not the present but a long-gone moment frozen in transit. Some of these galaxies may already be different than they appear, merged, consumed, or faded, but their light preserves them as they were. In this way, the border of the void becomes a museum of the cosmos past. And yet, despite the growing complexity, there is still an openness here that will vanish deeper into the web. Space remains vast enough for individual galaxies to lead solitary lives, for stars to age undisturbed, for the slow drift of matter to proceed without interruption. It is a liminal zone, neither the pure emptiness of the void nor the bustling density of the clusters, but a place of transition. To leave it entirely is to accept the return of noise, the gravitational chatter of many bodies, the turbulent exchanges of gas, the restless birth and death of stars. The path ahead will grow brighter, busier, and more chaotic. But for now, the view holds both, the silence of where we have been and the promise of where we are going. The edge is not a sharp line but a widening landscape, where the influence of the void is felt less with each passing light year. Eventually, its gravitational absence will be replaced by gravitational abundance, and the emptiness will no longer be the defining feature. The return is not a rejection of the void but a continuation of the journey it made possible. Without the stillness, the arrival would not feel like arrival at all. Here, in this threshold space, every faint glimmer ahead is a beacon. Every galaxy is an invitation to step further into the weave of creation. And somewhere beyond sight, the full chorus of the cosmos is waiting. The faint threads glimpsed on the void's edge now draw together into unmistakable strands. They are no longer hints or scattered bridges between lonely outposts. They are the beginnings of a vast architecture, a framework so large that it can only be seen in full from outside space and time. The filaments are not solid, yet their scale and presence defy the word fragile. They span hundreds of millions of light-years, their luminous points marking galaxies and clusters bound into a cosmic lattice. This is the web of light, the great skeleton of the universe, the structure that gravity has been weaving since the earliest moments after the Big Bang. It is both delicate and immense. From within, one can never see its whole form, but the repetition of its geometry becomes apparent. Galaxies line the threads like jewels strung along invisible cords, their arrangement not random but dictated by deep, ancient tides of matter and energy. The spaces between these filaments are not the pure, unbroken voids left behind. They are smaller pockets of darkness, still immense but hemmed in by luminous walls. Inside them, galaxies are rare and the silence still holds sway. Yet these pockets are shrinking as the web grows ever more intricate. Matter flows inward along the threads, pulled toward massive knots where several strands intersect. In these intersections lie superclusters, realms so dense with galaxies that their light blurs into a haze. They are cities of the cosmos, where the gravitational pull of thousands of galaxies locks them into a slow dance that may last until the universe grows cold. The sight of one from a distance is like seeing a city's lights at night from far above, an endless grid glowing in all directions, each point of brilliance the combined light of billions of suns. Approaching a filament reveals its paradoxical nature. Its true thickness is vast beyond imagination, tens of millions of light-years, but from inside, it feels like a corridor lined with galaxies that stretch ahead and behind in perfect perspective. Each galaxy spins in its own right, yet all are drifting in the same general direction, following the gentle slope of gravitational potential toward greater concentrations of mass. It is the quiet traffic of the cosmos, unhurried but unstoppable. Within these filaments, galaxies are closer together than in the lonely expanse near the void's edge. Interactions become more frequent. Some pass near enough to exchange streams of stars and gas, their mutual gravity warping each other's shapes. Others collide outright, merging into larger systems, triggering bursts of star formation as clouds of gas are shocked and compressed. These interactions are not chaotic destruction, but the engines of renewal. The web's light is constantly refreshed by the birth of new stars ignited in the aftermath of these encounters. The glow itself is deceptive. Much of the web's structure is invisible to the human eye, composed of dark matter that neither emits nor absorbs light but exerts an undeniable gravitational influence. Without it, the luminous parts of the web could not exist. They are simply the visible tracery of a much deeper scaffold. Astronomers map the dark structure indirectly by watching how it bends light from distant galaxies, a cosmic lensing that reveals the otherwise unseen. Between galaxies, the space is not empty. Wisps of intergalactic gas flow along the filaments, heated to millions of degrees by the collapse of matter into denser forms. This hot plasma emits faint X-rays, invisible to ordinary vision but detectable with the right instruments. It is the bloodstream of the web, carrying the raw ingredients for future stars from one node to another. Traveling deeper into the web, the density of light increases until there is no direction without galaxies in sight. The faint background haze becomes more prominent, a tapestry of distant systems overlapping in every direction. The cosmic microwave background, once so pristine and unbroken in the void, is now dimpled and distorted by the gravitational pull of massive structures. Light from the ancient universe takes longer, more winding paths to reach here, as if the web's weight bends even time itself. Despite its grandeur, the web is not eternal. It is a product of a universe still in motion, still expanding. In the far future, the accelerating expansion driven by dark energy will stretch the filaments thinner, pulling galaxies away from one another faster than gravity can hold them together. The web's intricate design will eventually unravel, its light islands set adrift into the deepening dark. But now, in this age, it is at its fullest expression, a living structure linking the farthest reaches of space. From the vantage of a single galaxy, the web's existence is almost impossible to comprehend. Stars rise and die without their inhabitants ever knowing they are part of something so vast. Civilizations, should they arise, might map their local group, perhaps even the supercluster, but the full weave lies far beyond their horizon. Only in aggregated data, collected across cosmic distances, does the pattern emerge. Yet here, drifting among the strands, it is possible to feel the geometry in a way that transcends maps. The repetition of form, the rhythm of light and dark, the gravitational pull toward nodes of brightness. Together they create a sense of being inside a design that is both natural and inevitable. The filaments are not built. They are grown, the result of physics playing out over billions of years, shaping matter in ways that seem almost organic. As motion carries forward along one of these luminous threads, the path leads inevitably toward a knot, a region where the light thickens into brilliance. Here the filaments converge, their galaxies falling inward toward a shared center of gravity. This is the heart of a supercluster, a gravitational metropolis where the density of matter is high enough to bind together thousands of galaxies despite the universe's expansion. The sight of it is overwhelming. It is not a single object but a swarm, each galaxy a unique form, spirals with sweeping arms, ellipticals with smooth halos, irregulars twisted by past collisions. They orbit a common center that may be marked by an immense dark matter halo or by several giant galaxies dominating the core. The combined light is enough to outshine entire regions of the cosmos, a beacon marking one of the great intersections of the universal web. In these knots, the process of cosmic evolution is at its most intense. Galaxies interact constantly, their shapes distorted by tidal forces, their stars stripped and scattered into the intergalactic medium. Massive black holes at the centers of some galaxies feed on inflowing gas, releasing energy in jets that can stretch for millions of light years. This energy shapes the surrounding environment, heating gas and slowing the birth of new stars, regulating the life cycle of the cluster itself. Beyond these intersections, the web stretches onward in all directions, its strands fading into the distance until they vanish into the horizon of the observable universe. And somewhere, far back along the path, lies the void from which this journey began. A place so empty that the existence of this living lattice seems almost impossible. Yet they are part of the same whole, opposites that define each other, two halves of the same cosmic truth.